Hello everyone, my name is Jannatul Firdaus. I am from Group 6 and today I'll presenting our project titled Connection of a Large Renewable Power Plant with a Pump Hydro Storage to the Australian National Grid. And the project focuses on how integrating renewable energy and storage can help stabilize the Australian grid as we move forward to a cleaner energy future. So here's a quick outline of what I'll cover. I'll start with the introduction and aim of our project, then walk through the design parameters, methodology, calculation, load flow analysis. After this, I'll discuss how we validated our result against the national electricity rules. And finally, I'll share our key findings and recommendations and conclusion. Here's the introduction. Australia's power system is rapidly transitioning to renewable like solar and wind. But the challenge is maintaining grid stability because renewable output fluctuated with weather and the time of the day. So here in the picture, we can see that the renewable energy, the uses of renewable energy increasing day by day. So that's where we need the pump hydro storage because renewable output fluctuated with weather and the time of the day. So that's why we need the pump hydro storage. It stores surplus renewable energy by pumping water to a higher reservoir and releases when demand is high. Our project explore how combining renewable with pump hydro can strengthen the national grid in terms of stability, reliability, and frequency control. So here's the aim and objective. The aim of our project was to analyze the connection of a large renewable power plant with pump hydro storage to the Australian grid using PSSC simulation. And our objectives are threefold. Build and simulate a detailed model in PSSC, evaluate load flow voltage and frequency stability under different operating conditions, ensure the system complies with the National Electricity Rule and AEMO standards. Here's come the methodology. The methodology followed five major steps. First, we define system and design parameters. Then we build the PSSC model and run base load flow. Next, we added both the solar PV and pump hydro modules. After that, we validated power flow across the grid connection. Finally, we checked compliance with the relevant Australian standards and documented all result. Next slide is design parameter. The system used 420 kilometer and 275 kilovolt transmission line operating at 50 Hz. The design minimizes transmission line losses while maintaining reliability. It reflects a typical high voltage link used for large renewable connection in Australia. Next one is load flow analysis. Load flow analysis was done in PSSC after connecting the renewable plant, pump hydro unit, and transmission line to the grid. We looked at voltage profiles, power flow direction, and line losses under steady state conditions. One key observation was how shunt capacitance affected bus voltage. Higher capacitance improved voltage levels, while lower capacitance causes drops. Finally, we calculated total system losses by comparing generated and load power, confirming overall system efficiency. And then the next one is calculation of power losses. This slide focuses on the calculation of power losses across the system. After connecting all major components, the renewable plant, pump hydro storage, and transmission line, we used PSSC load flow analysis to determine where energy losses occurs. The total losses were calculated by comparing the total generated power with the total load demand. Results showed that the losses remained within acceptable limits, mainly due to the 275 kilovolt transmission line, which helps minimize current flow and reduce the losses. This confirms that the system design is efficient and suitable for long distance power transfer. From the next slide, my team member Biplav will continue.
Thank you, Jannatul. Here we model the integration of a solar PV farm into a Australian national grid. The single line diagram illustrates how the PV plant connected through the transmission network to the main grid. This step allowed to us to observe the impact of renewable generation on voltage, power flow, and stability under different load conditions. The connection was designed to comply with AEMO and NER standards, ensuring that the PV system operates safely and reliably as part of the national grid. Okay. After integrating the PV from, we analyzed harmonic distortion to evaluate power quality. Most harmonic levels were within the NER limits, confirming good inverter performance. A few higher order harmonic were slightly above the standard range, which can be mitigated with harmonic filter or fine tuning of the inverter setting. Overall, the system maintained clean grid compatible voltage waveform. We then examine voltage flicker, which measure how fast voltage varies due to renewable fluctuation. The initial test exceeded the limit, so we carried out a stage 2 compliance analysis under both strong and weak grid conditions. The resulting short-term and long-term flicker index roughly 0.15 and 0.10 were well within NER planning limits. This means the solar farm won't cause noticeable flicker or voltage disturbance to consumer. The frequency response graph compares how the grid behaves with and without renewable integration. Without PV and hydro, frequency deviation was larger and took longer to recover. When both were added, the system stabilized faster and stayed within the zero point 0.5 plus minus frequency band allowed by NER. This shows that adding pumped hydro storage improves dynamic stability and frequency control during grid disturbance. Okay, this slide presents the critical clearing time results, the time a fault can persist before causing instability. Without renewable or hydro system, the CCT was short, showing less fault tolerance. With both systems connected, the CCT increased, indicating stronger transient stability and better system reliance during faults. The improvement is one of the key benefits of hybrid renewable setup. Finally, the exciter step test was used to assess voltage regulation. The voltage response remained smooth and oil damped, staying within the 10% variation limit set by NER. This proves that the system control loops and excitation mechanism perform effectively during sudden voltage changes. In short, the hybrid system satisfy NER voltage performance and stability standard across all tests. Sustainability. Study of sustainability. This study beyond technical performance, we also assess sustainability. This integrated system reduce carbon emission, maintain grid reliability, and directly support Australia's clean energy transmission goal. We recommend broader implementation of pumped hydro storage to support renewables high voltage transmission. 275 kilovolt and above should be used to minimize losses. Further studies could compare different storage technologies and explore long-term system impacts. And finally, closer coordinated with AEMO and NER will be essential during future grid upgrades. To wrap up, our PSSC simulation confirmed that integrating solar PV and pumped hydro storage meets NER standard and improves overall grid stability. The result shows this combination deliver cleaner, more reliable, and sustainable power for Australian future energy demand. This is our Gantt chart. Our Gantt chart outlines the project timeline from data collection and modeling to analysis and reporting, all completed within schedule. This is our references. The references include AEMO, Clean Energy Council, and Siemens PTI manual, which guided our design and analysis process. Thank you.
We'll be happy to take any questions.